The second part of the cosmology section is about the Big Bang model. So, to start with, you need to be familiar with the idea of the Doppler effect. Now, the Doppler effect is useful because it enables us to see some stars which have regular absorption lines, and we look at the absorption lines on the other stars which are from a cluster of galaxies which are moving away from us. We now know this line has been shifted here, this line has been shifted here, so basically the absorption spectrum has been shifted to the right, in other words, with an increasing wavelength. In other words, redshifting. So if we know the ratio of the change of wavelength compared to the original wavelength, we're able to find the ratio between the velocity, the recession velocity, and the speed of light. So why is the Doppler effect so important? In the 1920s, Edwin Hubble is famous for observing the spectrum of stars and galaxies that were very far away, and he noted that they were traveling away from us. They were redshifted. Imagine being in a playground and looking at everybody around you, and everybody appears to be running away from you. You can assume that in the past they were much closer to you in the past. In fact, an observation could be made that if they were twice as far away from you, they were actually going twice as fast. If you step that backwards, it probably means that they started pretty much where you are and all at the same time. So this redshift suggests that the universe is expanding. So Hubble. Some galaxies were blue shifted, some nearby galaxies, because there was a kind of random variation of galaxies, but most galaxies, especially the ones that are farther away, were redshifted. And what they noticed was the further away they were from us, the more redshifted they were, so the faster they were going. Conclusion is that therefore the further away from us they were, the faster they were moving. It's like an expanding ball, like this. The ones on the outside are moving fastest compared to the ones close to the center. You can see this velocity vector here, and there's a smaller velocity vector here. If they're going faster faster now, and these are going slower now, if we run that backwards, it basically means that they all pretty much started at the same point at the same time. So we say that both space and time originated with the occurrence of the Big Bang. One thing you should understand is that it's not like a balloon which is expanding outwards into an empty space. There is no empty space. There is no edge of the universe. So this is a concept which is difficult to understand sometimes. But you must understand that there is no edge, so they're not expanding. The universe is not expanding into an empty space, into a void. So it's not like a balloon. There is no edge to the universe. Now, at this point we combine space and time and energy and matter into the same kind of entity. It's all kind of wound in together. So as space-time is being created in between the stars and galaxies, this gives the idea that the galaxies are actually moving away. Space-time and space itself is expanding. So as space is expanding, the matter and energy are expanding with it. So the Big Bang model. There was a discovery in the 60s by these two American astronomers called Penzias and Wilson of the cosmic microwave background radiation, and this basically supported the idea of the Big Bang theory, and we'll look at that now. Okay, this background radiation, there were two other scientists that looked at the amount of helium that there was in the universe, and there was far too much. They knew that helium was created in stars, and you needed high temperatures for hydrogen fusion to produce the helium. Yet there was a lot of helium in the universe, and they knew it couldn't have come from stars. So there must have been some kind of cosmic event where the temperature was hot enough to produce so much helium. So at some time in the past, the universe was much hotter. With time, the universe expanded, and as the wavelength of this initial radiation expanded, the wavelength gets longer, and they predicted that there would be a background radiation of the original radiation, which from the original Big Bang, which would be equivalent to roughly 3 Kelvin now. Which part of the spectrum is this? This is the microwave part of the spectrum. So, meanwhile, Penzias and Wilson were doing some routine observations, and they discovered there was this interference, this signal that they couldn't get rid of. They tried all kind of ways to get rid of it, but it was always there. And then they contacted these other guys in Harvard and said, well, there's this background radiation, we can't get rid of it, what could it be? And then they understood that they'd actually discovered this famous background radiation, which was basically the afterglow of the Big Bang. And this is what it looks like, and it's uniform throughout the universe. So in every direction, there's this very low energy, very uniform radiation, which is called the 3 Kelvin background radiation, or the cosmic background radiation, or the microwave background. This is the black body curve. We have a microwave, which is basically the peak wavelength lambda max is 5 centimeters. So if you use the Wien's displacement law, you can find out what temperature the universe is at, this background temperature. What is it? And you'll find that it's around 3 Kelvin. Explain how cosmic radiation in the microwave region is consistent with the Big Bang. The syllabus says, a simple explanation in terms of the universe cooling down is all that is required. So, this background radiation, why is it evidence of the Big Bang? So, what we know is that now the universe is very, very cool. 3 Kelvin is not very warm. And so basically all the energy has been spread out and it's much cooler. In the past, it must have been hotter, and it must have been much more concentrated. With the expansion of the universe, the original wavelength, the original energy, the original radiation given out has been so redshifted it's gone into the microwave part of the spectrum. Another way of looking at it is that the hot matter that was there to start with, that was there to produce the helium, this abundance of helium, has now cooled down so much that we're now at 3 Kelvin. So the universe is now much bigger than it was 15 million years ago. So this energy has been degraded. So the Big Bang. The Big Bang is basically accepted theory for the origin and the evolution of our universe. It postulates that 12 to 14 billion years ago, the portion of the universe we see today was only a few millimeters across, and it expanded from this super hot dense state to the very much cooler cosmos that we see now. We can see remnants of this hot dense matter as this cold cosmic microwave background radiation that is all over the night sky. So the Big Bang. This is basically a singular point at which space, time, matter and energy were created, and the universe has been expanded ever since. What are the 3 points of evidence that we should know? The expansion of the universe. It appears that the universe is expanding because of this galactic redshift. We suggest that in the past it was much smaller because all these galaxies were moving away from us. The background radiation, this is basically evidence that there was a hot universe once upon a time, but now it's cooled so much and it's so redshifted that it's in the microwave part of the spectrum. This is a hot temperature that must have existed at one time. Another one is the abundance of helium in the universe. we know that the helium that is produced by stars cannot account for the abundance of helium that we have in the universe. Therefore, there was this cosmic event which produced lots of helium, and that where the temperature was hot enough to produce the helium. How does this provide a resolution to Olbers' paradox? Well, as we remember, that the assumption for Olbers' paradox was that the universe was eternal, infinite, and static. And then, if that's the case, there would be an infinite number of stars and the night sky would be bright, but it isn't. But if we consider the universe to be finite and expanding, the radiation received will be small and finite for two reasons. There's a finite number of stars that have a finite lifetime, so they don't radiate forever. And the second thing is, because the universe has a finite age, there are some stars that are so far away the light hasn't had chance to reach us. So, and this is also to do with the fact that the universe is expanding and it's got a finite age. Some of the light has not reached us because there hasn't been enough time for that to happen. Also, since it's expanding, some distant stars are redshifted so much, and they contain less energy, because if you use E is equal to HF, then that's going to have less energy.